Good day, everyone. We'll be discussing on process, threads, scheduling, quantum, and context switches on this particular video. Let's get started. Consider I'm using a server that has got only one CPU core on it. I'm listening to music using VLC Media Player, using OneNote, browsing internet, running SQL Server in the background. It will all be kind of seamless, wherein I'll be able to hear music, check OneNote. SQL Server can be accessed using SQL Server Management Studio, and then I can browse the internet all at the same time. But in reality, what happens is like a processor can execute only one thread at a time. It basically completes or it basically runs a thread, executes a thread on the processor, and then moves on to another thread. And the execution happens strictly one at a time. There is no way a processor can execute multiple threads at the same time. If we talk about process, a process is an encapsulation of one or more threads. Process in real world can be compared to a team which comprises of one or more team members who all have a common goal to achieve. So each member in the team will get a task they basically have to complete individually, which in turn will result in the final goal completion. A process is same as a team, wherein it has got several team members within it. So for example, a process is compared as a team and the team members are all compared as a thread. A process will have a process ID, memory space allocated to it, and doesn't do any actual work. It is basically a container uh, where threads will be present, and these threads basically performs all the work, like the threads within the process that performs the actual work. Let's take an example. Let's take Outlook as an example here, where while you are using Outlook, a thread will basically be responsible for sending and receiving emails. A thread will be there for an email that we are composing. One thread will be responsible for the spell checks, and another thread may be responsible for the rule check that is configured. And there can be many other threads for several other functionalities within Outlook. So in a nutshell, all these threads will be running in the background and make sure like all the functionalities within the Outlook is working fine. So Outlook is a process here, and then the individual functionality within Outlook gets executed by these threads. So let's look at one particular application. In our case, let's look at Edge. What I'll do is like I will download Process Explorer, and then what we can do is like we can look Edge within this Process Explorer. So if we open this Process Explorer tool, it basically shows you all the process that is running on this particular server. So let's get to Edge here. So maybe like let me minimize this one. And then we have Edge here. So what I'll do is like I will right click on msH.exe and then click on properties. We have several tabs associated with this process like image, performance, many other things. The one that I'm interested is threads, which we are discussing right now. So what we can see here is like there are so many threads associated with this application. So TID refers to the thread ID. So if we just look at one particular thread, we will be able to look at the stack for that particular thread. So as I told you earlier, process is just a container. It is the threads that is present within this process actually performs the work. So as far as MS Edge is concerned, this particular application holds this many threads that we are seeing here, and these individual threads actually performs the work. Yep, moving on. Let me close the Process Explorer. So how does CPU manage all these threads and schedule it for running? So each CPU will have a list of threads, and that needs to be executed in a list called ready list. CPU executes these threads using a first in, first out approach. That is, the thread that comes first is executed And once the execution is completed, it will be added back to the top of the list once the quantum of that particular thread is complete. So as an example, if we look at it again here, so right now we have a thread from VLC, a thread from Outlook, a thread from OneNote, and then a thread from Edge. So if we look at this particular diagram here, what we can see is like the thread with respect to Edge came first, next OneNote, next Outlook, and then next VLC. So what happens is like the thread associated with Edge gets executed on the CPU, and then once its quantum is over, what will happen is like this will be added at the top of the ready list, and then OneNote thread will be given a chance. And once that is executed for its given quantum, what it will basically do is like once the quantum is reached, it will go to the top of the list and get it added on top of the edge thread. And the same process happens for the other thread also. Yeah, this is how we will be having threads executing on a CPU. But just to understand, we are discussing about a server which has got only one CPU core. Okay, let's consider we have multiple CPUs on a server. So let's consider we have two CPUs, okay? Each CPU will have its own ready list and follows the same thread scheduling method as discussed previously. So in this diagram here, what we are able to see is like the first CPU is basically having a thread from VLC, Outlook, OneNote, and then from Edge. The second CPU is having a thread from Outlook, VLC, OneNote, Edge. So what happens is like each of these CPUs execute each of these threads, and once the thread reaches its quantum, it basically adds to the top of the ready list for that particular CPU. So that is how the scheduling happens as far as the CPU is concerned. Yep. So each of these application will basically tell Windows that it has this many number of threads, and then Windows will basically schedule these threads on all the available CPUs where possible. So now let's discuss quantum. Now, what is a quantum that we are discussing right now? Quantum is the time duration that a thread gets to execute on the CPU, after which it has to move away from the CPU and allow the CPU to be used by other threads and get it added to the last position of the CPU's ready list if it has more work to do. If all its work is done, so let's consider the thread which is executing on the CPU. If it has more work to do after it reaches its quantum, what it basically does is like it adds it to the top of the CPU ready list and then allows the next thread to execute. For example, once a thread reaches its quantum, let's consider there is no other work, like all the work associated with that thread is completed, then what happens is like it completes its quantum and then it moves away from the scheduling at all. Yep. Then it basically finishes and kind of moves away from the list altogether. So normally it is 4 milliseconds for every third and is dependent on operating system, CPU speed, and it normally varies between different CPU generation also. So if we look here, the thread executes for 4 milliseconds and then comes out of the CPU even though it needs more time to complete. This is called preemptive scheduling. Let's consider I have a thread which will complete all its work in maybe like 8 milliseconds. In this case, this thread will execute for 4 milliseconds, and after its quantum of 4 milliseconds is done, it will save its execution context on the CPU and moves out of the CPU and adds it to the top of the CPU's ready list and wait for its turn to again execute on the CPU. Now, once its turn comes, the thread restores its previous execution context from the CPU and then executes again on the CPU. This time, since it is considered like it will require only uh, 8 milliseconds, it has completed its first quantum, and then when it executes one more time, its second quantum of 4 milliseconds completes, and that means like it has completed 8 milliseconds, and that way it has completed all its work and it announces its completion and completely moves out of the CPU. For example, let's consider we have two let's consider we have two threads, T1 and T2 on the ready list, okay? And T1 executes on the CPU, and after 4 milliseconds, it basically yields and then adds it to the top of the CPU ready list. While T1 moves out of the CPU, it will save its execution context. Now, when T2, the thread 2 gets its chance, it will basically restores its execution context saved earlier and starts the execution on the CPU from where it actually left the last time. So this process of saving one's execution context and restoring another execution context is basically called context switching. Yep. We will speak about scheduling in terms of SQL Server on my next video. Thanks for watching. Have a great day. Jai Hind.